In the name of Almighty God, I'm Master Hassan Kosha, and today I want to talk about Introduction to Plasma Module. The plasma module is specifically designed for the modeling and simulation of both low temperature and equilibrium plasma systems. It empowers engineers and scientists to investigate discharge physics and assess the performance of both existing and conceptual plasma designs, supporting simulations in zero dimension, y dimension, two dimensional, and three dimensional. The plasma module addresses the complex and high nonlinear nature of plasma behavior, where even a small change in parameters like electrical input, pressure, or plasma chemistry can lead to significant variations in discharge characteristics. Plasma systems involve a wide range of interconnected physical phenomena, including fluid dynamics, reaction kinetics, heat and mass transfer, and electromagnetism. The plasma module offers specialized tools for accurately simulating both non-equilibrium and equilibrium discharges across a broad spectrum of engineering applications. It includes the first, a comprehensive suite of physics interfaces for building custom models. The second one is library of fully documented example models. And the third one is a detailed user manual to support both new and advanced users. The use of the Plasma module. The Plasma module provides advanced capabilities for simulating a wide range of plasma reactors and plasma-related surface processes relevant to both scientific research and engineering applications. The following section highlights several representative use cases. The module supports simulations of plasma sustained by various types of electromagnetic excitation sources in the low temperature cold plasma regime. Typical applications include: the first one is direct current discharge, the second one is inductively coupled plasmas. The third one is capacitively coupled plasmas, and the fourth one is microwave plasma, and the last one is dielectric barrier discharge. The plasma module also enables the simulation of plasma-enhanced surface processes, such as plasma-enhanced chemical vapor disposition. The next one is plasma-enhanced etching. In addition, the plasma module supports the modeling of equilibrium discharge, where all species share a common temperature and the plasma is assumed to be fully ionized. Direct current discharge. Direct current or DC discharges are typically sustained through secondary electron emission from the cathode, triggered by ion bombardment. Electrons emitted from the cathode are accelerated through the cathode fall region, gaining energy as they enter the bulk plasma. If they acquire sufficient energy, these electrons can ionize the background gas, producing new electron-ion pairs. The resulting electron travels toward the anode, while the ions immigrate back to the cathode, where they may generate additional secondary electrons. The discharge dynamics are such that most of the applied electric potential drops across the cathode pole region and narrow zone near the cathode. Within this region, electron density and flux increase exponentially. Under certain conditions, the cathode fall is followed by a region of weak electric field known as the positive column. In the positive column, the discharge becomes more uniform and the electron-ion pairs produced are primarily lost to the surrounding walls in the radial directions. The first figure shows electron density distribution in a DC argon discharge at zero point 0.5 torr or at a pressure and an apply of voltage of 125 volt. Inductively coupled plasmas. Inductively coupled plasmas, or ICPs, were initially developed in the 1960s as high-temperature thermal plasma for coating applications. These early systems operated near atmospheric pressure, producing gas temperatures on the order of 10,000 Kelvin by the 99 uh, 1919, the ICP technology transitioned into the semiconductor industry, where it became widely adopted for film processing and large area wafer fabrication. Modern ICP reactors operate in a low pressure range, typically between 0.002 and 1 torr, maintaining gas temperature close to the ambient conditions. Low pressure ICPs are favored for their ability to generate highly uniform plasma densities over large volumes and sustains high plasma densities, resulting in strong ion fluxes to wafer surfaces, which are critical for precise etching and deposition. From an electron standpoint, ICPs function similarly to transformers, with the driving coil acting as the primary winding and the plasma serving as the secondary, and an alternating current in the coil induces a time-varying magnetic field which generates currents within the plasma. The electron current in the plasma flows opposite to the coil current, inducing a reactive current back into the coil. Electron heating primarily occurs within the plasma's skin depths, which decreases as plasma density or driving frequency increases, thereby limiting the volume where power is deposited into the electrons. This picture shows a Seeley radical number density in an ICP reactor operating in a silane argon mixture at 13.56 MHz and 50 watt. Capacitively coupled plasmas. Capacitively coupled plasmas, or CCPs, are widely used in the semiconductor industry for thin film deposition and etching application. In typical industrial setups, the plasma is generated between parallel plate electrodes spaced about 3 cm apart, with electrode diameter often reaching 30 cm. These systems usually operate at frequencies ranging from 100 kHz to 100 MHz and at pressures between 2 and 200 Pascal. Although CCP sources can also operate at atmospheric pressure, doing so requires a much smaller discharge cap, typically on the order of a millimeter, to maintain a manageable pressure distance (PD) product and ensure stable discharge conditions. In CCP, discharge species dynamic can create regions of intense charge separation at the electrodes that are strongly time modulated. The so-called plasma sheaths within the sheath intenses electric fields, accelerate electrons to energies sufficient for ionization, thus sustaining the discharge. In contrast, the plasma bulk, the region between the sheaths, features a much weaker electric fields and tends to remain quasi-neutral with a minimal net charge. This picture shows a parallel average electron density in a GEC-CCP reactor operating at 13.56 MHz with 1 watt of power absorbed by the plasma. Thank you so much for watching my tutorial on video until the end, and also you can download the appropriate COMSOL simulation from my github.com/masterscript. Today is 15th of March 2026 and time is 9 o'clock at night.